student the course of physics of linear and nonlinear optical waveguides. So, today we have lecture number 29 and today we are going to learn about the power associated with the propagating mode. Okay. So, in the last class we have an idea that how the modes is propagating and for fundamental modes and higher order modes, how the interference of the phase bond play a role to construct the structure of mode, etc. In today's class, we will going to learn about the power associated, what is the amount of power, we are going to calculate rather, what is the power associated with a mode. So, the amount of power associated with a mode that we are going to calculate. So, in order to calculate that, first let us refresh our concept of pointing vector. So, pointing vector the pointing vector S was defined as E cross H. So, the wave propagating along z direction the wave propagating along z direction will have a form of E as this, that we already find, sorry, it is not E y, the general form is E vector E is equal to E of x e to the power I beta z minus omega t. So, for the wave that is propagating along z direction, in the waveguide that is normally the case, we consider the direction of propagation as z. So, electric field can be in this way, and for T mode TE mode we have E y as omega t. So, that is the structure of the field that we have during the propagation. Now, for real electric field, because electric field we know that electric field and magnetic field are real. So, for real electric field I can write this as, so for real electric field we have E y as E y x cos of beta z minus omega t. So, I just replace this exponential thing to cos, because the electric field is real, that we always, these things we can always do. So, this is the real electric field, and this real electric field is carrying some kind of power, and that we are going to calculate. Now, if this is my electric field, we have in our hand the Maxwell's equation, which says that curl of E should be equal to minus of mu 0 del H del T. So, I can replace this thing as I k cross E is equal to I mu 0 omega this, because I know that curl of these things for plane wave is equivalent to I k cross that we learned earlier, and del t, this operator can be replaced as minus of I omega for plane wave. These two identities we know, and that is used here. So, my H becomes, when we have this, my H becomes 1 divided by mu 0 omega, and then k cross this one. Now, I know my k, this is the general form, but in this case, in our case, for when the wave is propagating for the slab waveguide along z direction. So, the k, if it is propagating along z direction, I have beta z. So, the form of the k should be something like this, and also the electric field is for T mode, we know is this one. So, the k cross E is how much, because it is beta. So, beta E y, it should be z cross y. So, we have minus of beta E y, and then it should be along x direction. So, this is using the vector identity, I can have this. So, k cross E is this quantity. So, H is essentially, vector H is essentially minus of beta, then mu 0 omega, and then we have E y and x unit vector. So, I have my E, I have my H. So, what is my E? E I already have here for T mode, and my H I also calculate using the Maxwell's equation in this. So, my S is simply curl E cross H, not curl, is equal to E I already have and B I already have. So, it should be minus of beta divided by mu 0 omega, then E y square, and then I have y cross y unit vector cross x unit vector. So, eventually I have this quantity is nothing but beta E y square divided by mu 0 omega, and this quantity is minus of z, and this minus will going to absorb. So, I have z. So, my S, which is the pointing vector, is moving along z direction. So, that is again not a surprising result, but important thing is that I now have the value here, which basically tells me what is the amount of power it should carry when the propagation constant of the mode is beta with a frequency omega, and the electric field is E y square, and form of the electric field we know. Then what is the value of the pointing vector, what is the value of the power associated with the mode, one can calculate through this explicit expression of the pointing vector. That is the goal. So, now if I want to find out the average, because normally we do the average because this is a sinusoidal field. So, if I want to find only the average of whatever the expression we have, so I can simply have beta divided by mu 0 omega and the average of this quantity, because this is now having a time dependent part, and if I do the average over that, I should have, because it is a cost function. So, we know that when we make a cost function, it is a square of that. So, average of cos square whatever the function we have, then it should be half is the value of the average. So, because E square, if you find from here square, it is E y square cos square, and if I make a average of this cos square beta z minus omega t, then I have half term, and I have something which is x dependent, the distribution, and it should be like this. So, my pointing vector, the average of the pointing vector should come in this form. So, what is the meaning of that? So, that means it is the amount of I mean in terms of power. So, the amount of power that is carrying per unit area is this amount, because that is the definition of the pointing vector, amount of energy that is passing through per unit area per unit time. So, let me now write down the thing. So, in slab waveguide, so if I want to find out what is happening in the slab waveguide, so in slab waveguide, the power associated with the mode per unit length in y. That is important because it is a 3-dimensional thing. So, and y we take a extended up to infinity. So, per unit length of y, if I want to calculate what is the power, then P should be equal to half of beta and then mu 0 omega and then it should be integration to the entire mode field what we have, which is simply E y square function of x dx. This is the amount of power one should have that is associated with the mode per unit length of y. So, for symmetric mode, now for symmetric mode, Ey, we know what is Ey for slab waveguide. Ey as a function of x for symmetric mode is simply say some constant say A0. In our notation it is B, so better to written with whatever the notation we used earlier. So, it is B the peak value and cos of kappa x in the region x is less than A. And for outside that it was C e to the power of minus of alpha x and d e to the power of alpha x depending on the value of the region. So, when x is greater than A, when x is less than minus A, these are the two regions where we have expect an exponential decay. So, that was the distribution, field distribution. So, once again let me draw the structure and the field, and I had the mode distribution like this, something like that. This point is A, this is minus A, this is 0 and this axis is my x axis. So, now I need to find out what is the amount of power that mode should carry, because this mode distribution is known and expression is known. But before that we need to understand, because these constants are very important, B, C, D, I need to execute this constant and we know the boundary conditions. If I have certain boundary conditions here, then I can execute the constant. So, if I took these boundary conditions, so boundary condition 1, so boundary condition in short BC 1. So, what is the boundary condition 1 here? The boundary condition 1 here is simply that if I have the continuity condition here, so this is B of cos kappa A is equal to C e to the power of minus alpha A, and these two are constant because, and this constant can be written in a new name, say some name, say A0. This is one boundary condition, and after putting this boundary condition I can write the B and C in terms of a single constant A0. So, my B becomes A0 divided by cos of kappa A, and my C becomes A0 divided by e to the power of minus alpha A. These are the two values of A and B I have. Again in the left side I also have the same boundary condition, and if I put the same boundary condition again, at x equal to minus a, what we have? We have b of cos of minus kappa a, which is eventually b of cos of kappa a, is equal to d of e to the power of alpha x. And now b of cos of kappa I already defined in the earlier case is a. So, this is nothing but a 0 rather. So, I can have the value of d from this expression as a 0 divided by e to the power of alpha x. So, I have all the values b, c and d, which are the constants of these fields, in terms of a single constant a. Now, if I plot that, if I now write that the final field, then final field E y will be equal to a 0 divided by cos of kappa a and then cos of kappa x. This is for mod of x less than a. On the other hand, I have a 0 e to the power of minus of alpha x minus a and a 0 e to the power of alpha x minus a. This is for x greater than a and this is for x less than minus a. So, these are the three fields. Again I rewrite in terms of a single unknown constant a 0, a single unknown constant a 0. Now, what I do is this. Now, my power P is beta divided by 2 mu 0 omega integration of minus infinity to infinity E y square, which is a function of x over dx. So, this I can write, I can divide into 3 parts. So, I can divide these into 3 parts. So, this is part 1. So, from minus infinity, so this is goes to minus infinity to a. So, I have part 1 here, this is one part up to here, this is minus a to this is part 2 and last part is here goes to infinity plus infinity. So, this is part 3. So, the entire integration can be divided into 3 parts 1, 2 and 3, and if I write this, so let me write in bracket integration of minus infinity to minus a is the first part. When I write the first part, it should be a 0 square e to the power of minus no not minus 2 alpha, then x minus a, then dx. That is the first integral. Second integral, this is the one. Second integral is minus a to a. I have a 0 square divided by cos a square kappa a, because this is the new constant, this is the b basically, b square rather, cos a square kappa x dx. That is the second part of the integral, and the last part of integral plus a to infinity a 0 square e to the power of minus 2 alpha x minus a dx. So, all the three parts are, this is 1, this is 2 and this is 3. Three parts, 3 integrals we need to execute. So, 1 and 3 these parts are easy, because if you I mean if I go to minus infinity. So, the integral will be a 0 e to the power of minus alpha x minus a divided by 2 of alpha, and when I put these boundary conditions, that minus a and infinity. So, in minus a it should be 1 and infinity it should be 0. So, I can execute that quickly for both the cases and I can write. So, it should be beta divided by 2 mu 0 omega. I can execute this very quickly, and a 0 is common for all the cases. So, I can put a 0 out of that. So, a 0 square I can write, and then this integration is, as I mentioned, is 1 by it should be 1 by 2 alpha for this case, and here also if I execute it should be 1 by 2 alpha. And then I have the third. So, this is the results of integral 1, this is the result of integral 1, this is the result of integral 3, and result of integral 2 I need to calculate. Again, this is not a very hard thing to calculate. So, I can write it 1 divided by cos a square kappa a, and if I put a 2 sign here, then cos a square I can write is minus a to a 1 plus cos 2 kappa a and then dx. This is my equation, the integral 3. So, first two integral I already calculate, the last integral I need to calculate. So, I can simply calculate here, maybe I can do it in a different color. So, integral minus a to a 1 plus cos 2 kappa x dx, it should be simply 2a, and then the integration of the cos, it should be sine. So, I should have sine, and if I put this 2 I should have a 2 of that. So, 2 sine kappa of a, there should be a 2 here, 2 kappa of a divided by, during the integration the 2 kappa term will come out. So, this will be the value. So, eventually my power will be a 0 square beta divided by 2 mu 0 omega 1 by alpha, because 1 by 2 alpha plus 1 by 2 alpha I can write 1 by alpha, and the rest of the term is like that. So, it should be plus 1 by 2 of cos a square kappa a, which is already there, and then I have the integral value which I calculated here, 2a plus sine of 2 kappa a divided by kappa. So, precisely that is the result, but one can have a more compact result out of that, and that you can use by using that, you can find by using the boundary condition. So, let us do that quickly. So, my boundary condition 2 suggests, so B C 2 suggests minus of B, the derivative of is continuous. So, minus of B sin k a is equal to minus of C alpha e to the power of minus alpha a. Now, we already have B as a 0 of cos kappa a. This is we already have, and C is how much? A 0 from the boundary condition 1 I already have this. So, from BC 1 I already have this quantity, the value of A and B and C. If I put this, I simply have kappa of A0 will cancel out, minus minus will cancel out. So, A kappa tan of kappa A, because when you put kappa B here, then sin divided by cos term will appear, is equal to A0 alpha, e to the power minus a, e to the power minus of alpha I will going to cancel out. So, this additional condition I am having now. So, once we have this additional condition, I can make use of that in this equation, and may have some simplified form. So, let us find out. So, my P, if I put all this value, my P will be A0 square beta divided by 2 mu 0 omega 1 by alpha plus, I just simplify, I just put this second boundary condition, which is this one, to the equation, and I have this one plus A divided by cos square kappa A plus tan kappa A divided by kappa, that we have. Now, for fundamental mode, this quantity, this is a maxima and this is B according to my notation. So, it is better that everything I can have in terms of B, then it should be in terms of the amplitude, peak amplitude. So, that we can do, because B is A0 divided by cos of kappa A. So, that information I am going to use now. So, now my P will be A0 square beta divided by 2 mu 0 omega 1 plus alpha plus A cos square kappa A. I split it into two parts and then I can write it as tan square kappa A divided by alpha. I just replace this condition. So, kappa I can write from this equation. So, this I can find by using the equation kappa tan kappa A is equal to alpha. Once I have this, then I can write it as A0 square beta divided by 2 mu 0 omega, and then I can have 1 by alpha common. If I have 1 by alpha common, then it should be 1 plus tan square kappa A, and 1 plus tan square kappa A is eventually 1 by cos square kappa A. So, this is the first term, and the second term we already have as A divided by cos square kappa A. So, I can take this kappa cos square kappa A common from both the sides, and I have A0 square divided by cos square kappa A multiplied by beta divided by 2 mu 0 omega as A plus 1 by alpha. So, that is more compact form, and this quantity now this should be A square. Now, I can write as a peak amplitude. So, my power eventually have a more compact form, which is B square beta whole divided by 2 of mu 0 omega and then A plus 1 by alpha. So, this is the power associated with a mode when it is propagating inside a medium having a propagation constant beta, and if this alpha and A are the parameter that one can define for the waveguide, and then you can readily calculate what is the value of power, and it obviously it should be proportional to the peak value of the fundamental mode, peak value of the symmetric mode, which is B, and it is proportional to B square. Well, with this note I like to conclude. So, thank you for your attention. See you in the next class. In the next class maybe we are going to start a new topic, which is the modes in optical fiber, which is very important to understand. So, thank you and see you in the next class.